Number 5. So basically the last one on worksheet 2.
That's weird.
Just like the process, because it was a little bit different. It was like Mr. Cool, I'm turning off the lights.
Thanks.
If you wanted to know.
All right, so it says you deposit $10,500 into account that pays 10.3% interest compounded daily. Write the exponential model, yada, yada, yada. So the model that we're using is here. It says A and T are independent dependent variables. So in place for P, that's the initial amount or initial investment. Is at $10,500. R is the interest rate as a decimal, so 0.103. Again, you take a percent and divide it by 100 to convert it to a decimal. Compounded daily, I'm going to just do 365 for days in a year. So there's my model. Part B says to find the account's value after 7 years and 3 months. So I need to convert that into just years. So how much of a year is 3 months? Yeah, it's a quarter of a year, right? Because there's 12 months in a year. 3 divided by 12 is 0.25. So we're just going to plug that in for T. Go to my calculator. 10,500 times 1 plus 0.103 divided by 365 to the 365 times 7.25. And I get $22,154.04. And then part C asks, how long until the account is worth $1 million? So the way we do this is by graphing. So I'm going to graph 1 million in one spot, and then my function from part A in the other spot. Now I'm going to fix a window so I can see this intersection. Remember, x is representing time, so the minimum time is 0. And the maximum time, I just need to make sure that it's going to be long enough for it to get to 100. I don't really have a good idea of when that's going to be, but after 7 years, I got, basically, we doubled our value. I'm going to hope that within 100 years, that'll get to $1 million. But I don't know. That's probably fine. If it's not fine, we can always go back and make that a bigger number. The Y minimum is the initial investment. I'm just going to round that to 10,000 instead of 10,500. The maximum Y value needs to be bigger than $1 million, so I'm just going to do like 1.5 million. And let's take a look at that. So there's my 1 million line. Here's my account value. Definitely had it well within 100 years, so that's good. So I just need to find that intersection. To do that, I'll press second and then the trace button and select the intersect command. And since I only have 2 things graphed and they're only intersecting one time, I can just Press enter 3 times. And it tells me the X value is 44.2 years. That's not bad. Put $10,000 away, and 4 years later, you got $1 million.
What? Is that real?
I mean, 10% is a pretty good return on an investment. But yeah, it's real.
We should invest in a taco stand. Eating is cool.
Restaurants are one of the worst investments.
Makes sense. Actually does make sense.
They fail almost certainly.
What's the best investment?
In terms of like stability,
Yeah, like just being like staying safe, but also making some type of
Government bonds.
like huge corporations.
Government bonds. I know that AP account.
Government bonds are extremely safe, but their return is pretty low.
What they're saying. Mr. Osaki would be so
If you're talking about like a business, like something that someone, I think that rental, like housing, is typically pretty safe.
real estate,
Real estate is pretty safe.
making bank.
Megan,
How did you get 7.25? Like I get that it's 7 years and 2 months, but like how did you get that?
how many months are there in a year?
12.
3 divided by 12 is 0.05.
Once in the year,
Like 14.
Is that cool?
that's the only difference.
That's it.
I think you're at NDP.
You learn there 10 months in the year.
You thought there were 10 months in a year.
It's like 13, right? 13.
There's that mystery month,
Facts.
Is that leap month?
the leap month. Yeah, that's a rough year when you get a whole extra month.
Oh, wait, we did have an extra month. Do you think that go towards the school year or towards summer?
Summer.
You're asking like the weirdest hypothetical questions.
It's good hypothetical question. It could happen. Based off of like.
It could never happen.
Yeah, like there's a giant cataclysm and the orbit of the sun, of the Earth is radically different.
Because if you think about it, like photosynthesis and hypertonic osmosis.
Now you're just talking about the longest words you can think of.
Yes.
Joe thought chocolate milk came from brown cow.
All right, let's move on here.
You're not going to talk to everyone.
So, in the last lesson, one of the things we talked about was this, these two models, right? And you'll notice that really they're the same model. That if I take that compound interest and put R equal, or put N equal to 1, I get that general growth or decay model, right? Everybody see that? Is that okay?
Yeah.
Right, if N equals 1, these are the same thing, right? Okay, so this was kind of a big development because now what we've done is we've described a way, with the general exponential growth or decay, it's kind of assuming that nothing happens and then all of a sudden one day of the year, like all the change happens all at once. And then nothing happens, and like a year later, all of the change happens all at once, which doesn't really make a lot of sense for most things, right? So we developed this compound interest formula where, depending on the value of N, you could have like nothing happens for a while, we pay out part of the change, and then nothing happens for a little while, we get a little bit more change, and by the end of the year, that changes monthly, once a month we get a little bit of change. At the end of the year we have the same total change that we would have. Is that okay there? But that still doesn't really describe realistically a lot of systems, right? So let's think about like a biological system, like a population of organisms. Okay? So let's say human beings. How many human beings are there on the planet? More or less.
7 billion.
7 billion. Okay. So if we're talking about the population of humans on Earth, there's 7 billion of them. Now, what has to happen for the population to grow?
We gotta make babies.
Babies are born. Great. What would have to happen for the population to shrink?
We have to kill people.
People die. Great. And if the overall population is growing, that means more babies are being born than people are dying. And if the population is shrinking, there's more people dying than are babies born. Right? Now, when are babies born?
All year round.
All year round. Okay, so like the first Monday of the month, all the babies are born?
Yeah. We can say around that time.
So so everybody's birthday is like the first of the month.
Okay, no.
Every second.
It's random.
Every day.
Every day, okay, so just at what, at like
All day.
12:01?
All
Born
day,
every
every
second,
day.
People are born at random times.
So they're only born on the whole second? Nobody's born at like half a second?
Like every I don't know. All
You're going in the right direction.
like all day.
Is that white shirt on the side of your desk?
Yes.
That's awesome.
Wait, Mr. Cook, are you talking about probability now?
No,
Okay.
I'm just talking about what can happen.
Okay, so babies can be born at any time, any day, at any second, whenever they want, how they want,
With whoever.
with whoever.
Okay. And the same thing would go with death, right? They could be happening at any time.
Yes.
Okay. So if we want to then accurately describe a population of organisms, they're growing potentially all the time, right? Or shrinking, right? Depending on whether the population is growing or shrinking. But it could be happening all the time. How many compounds a year are we talking about then?
Oh, a lot.
A lot. Okay. What kind of number? Probably more than that.
You think trillions?
Probably more.
Quadrillions?
Probably more.
Quintillions?
That's not a thing. Infinity, right? If literally any time that population could change, then we really need infinitely many compounds per year, right? At every instant, something could be changing. We're interested in what if that number of compounds is infinite? That's what we're kind of interested in. Because it really describes a lot of systems, right? Most things, most real life, like biological or physical systems, kind of the change isn't happening just like in increments every once in a while. It's kind of always changing. So let's do this. Let's pick P to be 1, R to be 1, and T to be 1. And then let's see what happens when n goes to infinity.
Mr. Cooley, what
Yes.
does the first thing say? Like before the P was
Let.
Oh.
So can we just plug infinity in for n and type that into our calculator or something?
Yeah, there's 100%.
Yeah, there's definitely not.
There is?
No, we can't plug infinity into our calculator. But what we will do, or what we can do, is we can kind of approximate what's going on just by picking subsequently larger and larger values for n. So what I'm going to do is I'm going to just use like powers of n. Or powers of 10 as my values for n. So we're going to do like 10 to the 0, that's just 1, and then 10 to the first, 10 to the second, 10 to the third, and we're just going to kind of plug these into that 1 plus 1 over n to the n, and just kind of see what happens. Is everybody okay so far with that idea? So 1 plus 1 over n. So when I plug 1 in for n, I get 2. When I plug 10 in for n, I get 5.29 and change. Notice that from going from 1 to 2, not much changed, right? You didn't get a lot more growth. To go from 10 to 100, we went from 2.59-ish to 2.7-ish. Even less change, right? To go from 100 to 1,000, we went from 2.70-ish to 2.71-ish. So notice the first two digits are now the same, right? 0.27 has stayed the same going from each one. And going from 1,000 to 10,000, 2.71 has all stayed the same. So the first three digits are now the same. Everybody agree? So each time we get the n goes up, it's still getting bigger, but more and more of that number is kind of staying the same, right? So going from 10,000 to 100,000, 2.78 is now all the same, the first four digits. And we go again, and now the first 5 digits have all stayed the same. And we can kind of continue doing this, and eventually, no matter how we're running into a little bit of a no matter how big of an n you pick, it's still gonna, that number is still gonna get a little bit bigger, right? But more and more of it's gonna stay the same. Like up to here, we have, I don't know, what looks like 10 or 12 decimal places that are all the same, but after this 3, they differ. You guys see that? But what this is doing is it's basically showing us that as n gets really, really big, we are settling down to some value. There has to be like some upper bound to this number. It's not growing infinitely large. You guys kind of see that? That we put in bigger and bigger and bigger and bigger values of n, but the number itself has remained relatively small. It's still close to the 2.7. So, how many decimal places do you think this number is going to have? Infinite. Very good. Because as you pick a bigger and bigger value of n, which you can do forever, right? Because you can pick an infinitely large number, you're going to get more decimal places to remain the same, but you can always pick a bigger n, so you can always find more decimal places. Okay. And if I look at these numbers, this 2.718282053, yada, 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 did you guys see any pattern in how those digits are occurring? Is there any like repeating pattern amongst those digits?
Do they all start with the 7?
No, I'm not talking about in this column. I'm talking about like the numbers in this like the digits in this number.
Is there a way you can zoom in a little bit or no?
Doesn't really look like it, right? Okay. So what kind of number has an infinite number of digits and there's no repeating pattern to those digits? There's a special name for this kind of a number. So pi is an example of that kind of number. It's actually called an irrational number. So pi is an example. Some other examples are like the square root of 2, or the square root of 3, or the square root of 5, are also examples of irrational numbers. Notice one thing about all of these irrational numbers. We never actually say the number. We give that number a name because the number is infinitely many digits, and there's no repeating pattern to it. So like, nobody's about ready to list all the digits because you can't. So we give it a name. We're going to give this number a name as well. We're going to call this number E. So we're going to use the lowercase letter E to represent this number. We'll sometimes call this number the natural base. Or sometimes we'll call this Euler's number, in that it's named after the mathematician Leonard Euler, who did a lot of this development work that we're kind of talking about right now. He's on the wall of fame back there, on the far right, third from the bottom, or third up from the bottom.
Who's the greatest mathematician of all time?
Mr. Cooler.
That's a tough question, because like inherently, like what you did, you know, like what if somebody in the future does is based on what somebody from the past has already done.
That makes sense.
So like that's a tough question to ask. I mean, like, you know, Carl Gauss would be a decent answer, and that he had like major contributions to a lot of different areas of mathematics.
Oh, okay.
He was the guy that proved the fundamental theorem of algebra, that every polynomial has a solution.
How do you do that?
It was difficult in that many of the best mathematicians of his age failed to do that, were unable to tried and were unable to do it.
And they didn't even have calculators then.
They had no calculators. Right. This was in the 17 or 1800s.
That's a different type of smart. That is really that is crazy.
Yeah.
Hey, you'll be on that wall one day.
No, but
He'll be on the one with the marine chemist.
Oh, actually, you should go to NASA. I can see you doing like a work for NASA. There's a mathematician there.
Thanks.
Yes, sir.
All right. So what this becomes then is it allows us to make a new model. So we have this new number E. We can use when we have a system that's changing all the time. So some more examples of situations where change would be really happening all the time. We've talked about like in a biological system where you have a population. That population is going to be growing or shrinking kind of all the time. Another example could be radioactive decay. I think a lot of us are in a chemistry or earth science class and have probably at least heard that phrase before? So the idea is that you have certain elements will emit some energy or possibly mass to become either a lighter version of the same element called an isotope, or, depending on the type of radiation, might become a whole new element. And this radioactive decay is happening all the time. Imagine if you had a 1 gram sample of some substance. Each atom is undergoing radioactive decay, and those of you in chemistry know that like even a gram of something is like an enormous amount of atoms, right? You have like Avogadro's number, almost that. So 10 to the 23rd, just an enormous amount of atoms going on in that tiny little sample. Each of them doing radioactive decay. So at some point, one of them is emitting some kind of radiation, basically all the time, right? Another situation might be, so an like an electrical circuit, you have something called a capacitor that you'll use to like temporarily, like very short term, store electricity so that you can like change voltage or amperage in an electrical circuit. So like electricity comes down, it goes into this capacitor, it builds up, and then the capacitor releases that electricity, but it releases it at like a different amperage or voltage or whatever. And the release that happens is something that's exponential, and it's going to be continuous. Like it's going to always be, like at any instant, it's going to be releasing that electrical charge. And you have lots of other, systems in which things could kind of be changing continuously. You could even apply this into a compound interest situation. So let's say you invest, $1,000 at 6.5% interest, compounded continuously. And that continuously is the key word there that tells us that instead of using our old compound interest model, instead we want to use this new model. And then we can answer the same kinds of questions that we might have asked before, like what is the account's value after 5 years, or how long would it take for this to be worth $10,000 or whatever. What do you?
So in the calculator, it automatically knows that E is 2.71287.
Yeah. So on your calculator, if you wanted to say find the value of this account in like 5 years, we would do 1,000 times. If you look on the left-hand side of the calculator, you see a button that says LN on it. Above that button in blue is a symbol that says e to the x. So if you press second and LN, it's going to put in that number e with the exponent. And then you can type in like 0.065, and then if you said 10 years, we can put 10 in for t. And there we go. So yes, that number for E is built into our calculator. Just like the number pi is built into our calculator, the number for the square root of 2 is built into our calculator. This number for E is built into our calculator.
Mr. Cooler,
Yes.
kind of off topic, but it is on topic.
Okay.
I think in the future, like way down the line, we'll be able to plug in like full formulas into calculators to solve for formulas. Like the really, really complex ones, or no? Or do they already have that?
Very good.
Oh, they do.
You can buy a calculator on the market. Well, you just have to find one that has like the computer algebra system built into it. But a lot of them have solvers built into it, and you can solve univariable problems.
So like all the stuff you learned this semester is a calculator that can solve all that.
Yeah.
That is crazy.
Nothing like a $500 calculator.
That's probably, it's not that. I mean, it's probably $60 or $70 more than the base price for like the one that you're holding. But not much. But those are ones that are not allowed to use on like the ACT and stuff, and like probably couldn't use in your college math class. I would be suspect about you using it here, but I'm so picky about showing work that it's not that big of a deal.
Right, because you wouldn't even. But like an ACT, that would be a thing.
Well, you're not allowed. They're like on the banned calculator list.
Oh, really?
Yeah.
That's up after.
But there's like a whole branch of mathematics dedicated to like computational, like how can I build a machine to kind of solve this problem. Most of that interest is built around trying to solve polynomials, because that's a skill that we saw earlier can be quite complicated. We were looking at cases where it's like easy to really solve them and was still quite complicated. But there's a whole branch of mathematics interested in that. It has a lot to do with cryptography.
Oh, yeah.
So like, if you want to, like, you know how you send an email?
Yeah.
And like, if somebody intercepts your email, you wouldn't want them to be able to read your email. So it's like encoded.
Okay.
So like, if the person that intercepts your email gets it and looks at it, it's just like a bunch of polygon. It doesn't make any sense.
Right. Okay.
But if you have the, like if you go through the other end, the receiver's end, and you open their account, like it makes sense again. Like your message is uncoded.
That's cool. And that's all programming, right?
The systems are designed from a mathematics perspective, but it's like the computer does all of that automatically.
Don't you do that? Aren't you doing that right now? You're the program that you're making.
It has nothing to do with cryptography, but it is designed to solve a mathematics problem.
Are you close to solving it?
I mean, my program works, it's just really slow, so I'm trying to get it to go faster.
Nice. Okay, finish. Go ahead. I didn't mean to disrupt this.
Okay. So that's nothing really new. It's the same set of skills that we developed last time, right? We're just applying it. We just have a new formula or a new model that we can use also. You guys okay with that? And the time where we use that new model is where that change is happening all the time. So that means in a compound interest situation, the words continuously you should see, or it's related to like a real life biological or science kind of situation where like a population is growing or there's radioactive decay going on would be a common one I might use. The other thing that we can do with this is we can graph exponential functions using E. So last time we talked about exponential functions that were kind of written in this form, this general form. Any exponential function that's written in this form could also write in this form. Now, I'm not going to ask you guys, and it's beyond the scope of this class, to kind of convert back and forth between these two forms. I wouldn't ask you to do that. But it is something that's possible. If we take something in this form, notice there's no, the base, the exponential base is always the same. It's always e. So the way that we determine growth and decay is going to be a little bit different. So this time, to determine whether we're talking growth or decay, we're looking at the coefficient and the exponent, and then the leading coefficient for the problem. And then virtually everything else, though, is going to be the same as what we did before. So let's say that we wanted to graph I don't know why I wrote a T there. I want to write an X. So I would start by writing my values for A, B, and then K. Okay.
What's after the 1.5?
That's an X. And then since the A is positive and the B is positive, know that this is growth, just using the rule that I wrote down a moment ago. The horizontal asymptote is still y equals k. And then before, to choose our x's, we did h minus 2, h minus 1, h plus 1, h plus 2. You guys remember that? In this problem, though, we have no h. So what are we going to do? We're just going to do minus 2, minus 1, 0, 1, and 2. So anytime you have e as the base there, we're just going to use those x's. Okay? To find the y's, we'll do it the same way. We'll go back and just plug those into our function. So 2 times, then I'll press second and ln to get the e, 1.5 times negative 2, and then minus 3. So that's 2.9, and then we'll go back in and change the minus 2 to a minus 1, and then change it to a 0. And again, you're going to get like yucky decimals for almost all of these. That's okay. Just round it to like the 10th spot is usually fine. Maybe you might have, depending on how big or small they are, you might want to do something different. But, you know, it's probably fine. There's my table of values, and just like before, do this the same way. So make an XY-axis.
So it's very similar to the first, like homework one,
Yeah, it's basically identical, right?
same process.
The only thing that changes is the way you determine whether it's growth or decay, and then choosing the x's in your table. So you just drop the h part. So drawing my horizontal asymptote, and I just plot my points. Now notice that 237 is kind of an absurd point to want to try to put on here. I'm just going to kind of skip that one. So I'm just not going to graph that point because it just was too many tick marks to make. It was too big relative to everything else. So I just omitted it from my picture. I left it in my table. There's nothing wrong with doing that, but if you have one point at the end that you're like, yeah, that's just too big, that's okay. And then just like before, the domain is still going to be all real numbers because it's an exponential function. And the range is still going to depend on a and k. Since the a is positive, we're still going to go from k to positive infinity, just like we did before. So if we look at this lesson as a whole, like nothing really changed from what we did in lessons 1 and 2, right? The graphing is still basically the same idea. The way we use the model, it's a new model, but it's basically the same techniques, right? We write our model, plug stuff into it, or like graph it when we try to find what it's equal to. Same ideas. So this is where I'm going to end.